I'd like to wish you a very good day. PTQ Magazine and Digital Refining are pleased to bring you this webinar featuring Tracerco. My name is Ken Mollet. I'll be acting as your facilitator today. I would like to turn things over to Logan Boatwright from Tracerco to lead us into our subject. Logan, I'm going to turn off my camera and I will turn things over to you.
All right. Well, thank you very much, Ken, for the introduction, and thank you, everybody, for attending. On behalf of everyone at Tracerco and myself, we want to thank you for joining our webinar on non-contact interface measurement in refining, where we'll be introducing a new Tracerco product called Drum Vision, which utilizes neutron backscatter technology. So let's kick it off. Why does precision interface measurement matter? Well, interface position governs separation efficiency, chemical usage, and product quality. Poor or unstable measurements lead to conservative operation, overdosing, and unplanned upsets. In high temperature, fouling, or foaming services, many conventional instruments degrade or fail entirely. Essentially, without precision interface measurement, you have no control or vision into what you need to see. As you're all aware, precision interface measurement improves product quality, leads to less unplanned upsets, and reduces the failures in your facility. Going to go ahead and give an overview of the agenda that we're going to be covering today. First of all, why interface measurement fails in refinery service. We are going to go over the existing technology landscape and go over the strengths and limitations of some of the different technologies. And then we're going to discuss neutron backscatter. First is the technology, then give some examples of how we currently use neutron backscatter. And then we're going to introduce our new product called Drum Vision. After this, we're going to go over a couple of applications in refining, specifically delayed coking and distillation, and how Drum Vision can be used in those applications. We're also going to cover the operational benefits, safety, and economic impact. And then we will have some Q&A. So if at any point you have a question or anything you want to say, like Ken said, please type it into the chat and we will get to them towards the end. And I'll go ahead and kick us off. My name's Logan Boatwright. I'm a business development manager for the Measurement Instruments Groups. I'm located in Houston, Texas area, where our Pasadena office is located. I've been with Tracerco for about 5 months, and I've been in the oil and gas industry for about 17 years. I'll hand it over to Bailey and let him introduce himself as well.
Thanks, Logan. I'm Bailey Stainsby. I'm a physicist with Tracerco. I work in the research and development section of the business. I've been with the business for 5 years and I've been overseeing the project, the Drum Vision work and other parts as well. I'll hand over to Neil to introduce himself now. Cheers.
Hi, good morning, good afternoon, everybody. I'm Neil Murch. I'm head of sales for Eastern Hemisphere for Tracerco's Instrument Business Unit. I've been with the company for nearly 13 years now. I've over 20 years experience in the oil and gas industry, and I'm essentially the subject matter expert for nucleonic instrumentation for the business.
Thank you guys very much. We will go ahead and move along. So why does interface measurement fail in refinery service? Well, we all know that our industry isn't clean, especially in refineries. Things are dirty, process conditions fluctuate. We work in the elements, hot, cold, humid, any combination of any element you can think of. Process conditions also contribute to this as they're ever changing. The inputs change, the desired outputs change, process upsets happen. Fouling, emulsions, changes in DP. And look, throughout all this, we rely on instruments to tell us what our interface measurements are. But how reliable are these instruments? Are they measuring what we need them to measure? And how can we take the data that we get from these instruments and actually use it? So going into the technology landscape, we have a few listed on here. There are a few others. These are the ones that we wanted to focus on. We have the technology, the principle, the typical limitations, and the impact. And I want to say, first of all, that no technology is universally bad, but many technologies are operating outside of the conditions that they were designed for. So this slide here isn't to say that these technologies don't work, but are they the right technologies for your application? And do they give you just a piece of the puzzle that you need, or do they give you the whole picture? I'm not going to sit here and read through the ins and outs of each of these, but let's take guided wave radar, for example. If you take a look at some of the limitations, like fouling or emotion and foam distorting the reflection, certain conditions like coking or fouling can degrade accuracy, and the probes do require cleaning over time. This can all lead to unstable level indication or missed interface transitions. Gamma is another one. Gamma at the bottom of your screen there is a great technology. Tracerco uses this technology in both our instruments and in our services, but it does also come with some limitations. Primarily that externally mounted gamma cannot distinguish interfaces on large diameter vessels and works more like a point on-off switch in many applications. Each of these technologies relies on a physical property that's unstable in an operational refining environment. Neutron backscatter changes this by measuring hydrogen content through the vessel wall, providing a stable, non-contact, real-time interface measurement. Speaking of neutron backscatter, I'm going to invite Bailey back on the screen to go over the fundamentals of this technology.
Thanks, Logan. So I'm going to talk about the fundamentals of neutron backscatter. So neutron backscatter is a non-intrusive method of enabling the user to see behind the vessel wall and identify process materials. So what we do is we use a neutron source which is based next to a detector external to the vessel wall. This neutron source emits fast neutrons. These fast neutrons are hard to detect and don't interact with many materials. They interact with materials such as hydrogen due to neutrons having the same mass as hydrogen. So therefore, materials are actually distinguished by the level of hydrogen they've got in them. So for example, water will be easily distinguished against air because water has a lot more hydrogen than air does. So once these neutrons interact with the hydrogen atoms, the fast neutrons slow down and become what we call thermal neutrons. We call them thermal neutrons because they're in thermal equilibrium with the materials and the phases around them. And once they do interact with the hydrogen and the materials, these neutrons actually scatter. And in some cases, they scatter backwards. With materials with high hydrogen concentration, we expect to see a lot more neutrons scattered back than we would in materials with low hydrogen concentrations. So there's two diagrams here that sort of show that. We've got a diagram on the left which shows a low hydrogen concentration, which in this case we could say is an air or hydrocarbon gas. And then on the right-hand side, we've got high hydrogen concentration. So this could be water with a high hydrogen concentration in it. You can see on the left-hand side, there's a lot more neutrons emitted into this material, but there's not a lot of backscatter or scatter in general. On the right-hand side, we look at the material that we would say is water, for example, and there's a lot more scatter and backscatter, which is then scattered into the detector. So we can say the more hydrogen present in the phase, the more neutrons that are backscattered. These neutrons don't actually get too far into the vessel, so they go about 200 to 300 millimeters into the vessel. This device being a fixed gauge that's external to the corker or any other vessel that we're interested in seeing, and is actually placed quite close to the drum. So these neutrons are emitted in and come back out, and that's how we can distinguish between the phases. I'll hand back over to Logan now, and he'll talk about the current neutron backscatter usage.
Yeah, thanks, Bailey. So we wanted to give a quick background on what neutron backscatter is, and now we're going to show you how we currently use the technology, or historically use the technology at Tracerco. We currently use neutron backscatter in many of our services that are provided by our process diagnostics team. We have a little video that we're going to play for you here that's an animation. So in this case, we have a neutron head on the end of a telescoping pole. In the head is a high-energy neutron emitting source in tandem with a low-energy neutron detector. When we take this head and we place it on the side of a vessel, on an atomic level, steel and other materials are a relatively empty space, giving little to no resistance for the neutrons to pass through. Upon contacting hydrogenous material, the high-energy neutrons will lose energy and be repelled back to the low-energy detector, thus defining the term neutron backscatter. As the neutron comes in contact with more hydrogen within the vessel, they lose energy and will be sent back to the detector in higher numbers. The difference in the reading of hydrogen content allows us to tell with certainty where the different interfaces are within the vessel. You see listed on the screen some of the neutron backscatter applications that are currently major applications for this neutron backscatter technology. These are the most common applications where our process diagnostics team performs our services using neutron backscatter. Of course, in all of these services, you need to detect a level or an interface. So we have delayed cokers, tower bottoms, storage tanks, separators, desalters, coalescers, dehydrators. And again, historically, we've used the neutron backscatter that we just saw the animation of to perform a one-time service on these types of vessels. So here we have a brief illustration of how neutron backscatter can be used on a storage tank. In this case, you can see we've identified a clear vapor at the top, a bulk oil level, an emulsion layer, water, and a solids deposit in the bottom of the tank. Based on the hydrogen content of each material in the vessel, we're able to identify different phases of material and at exactly what level they occur. So we covered neutron backscatter as a technology, talked a little bit about some of the uses of neutron backscatter, and now Bailey's going to introduce Drum Vision, which is a new product that we have launched here at Tracerco.
Thanks, Logan. So Tracerco, as Logan just said, have created a product using neutron backscatter, and this enables us to visualize what's behind a vessel wall. So what we're looking to do is maximize process profitability. We're looking at optimizing yields, reducing waste, and increasing throughput. We do this by enabling high heated temperatures and low drum pressures. So the Tracerco Drum Vision supports more aggressive, profitable operating conditions. It allows for better feedstock, blending improves the coke quality as well. Next, we look at protecting your people and assets. So the Tracerco Drum Vision product offers real-time foam and phase detection, helping avoid foam overs, costly upsets, and unplanned downtime. As you can see on the right-hand side, we've got a sort of representation of a coker, and then there's 4 points labelled on there, which would be the Drum Vision product. So at different points, we can visualise different phases of process materials behind the wall. And one of the key ones that we're sort of interested in is the foam. So this then leads us on to reducing the operating costs. So as we're able to give a good informative idea of where the foam is in the vessel, it allows the user to cut chemical usage with anti-foaming agents. It means there's less energy waste and there's less unnecessary downtime. And finally, we look at 3-phase visibility. So as mentioned, we're trying to identify different phases. We're able to identify differences between water, vapors, corks, foams, things like that. So next, we want to see the product. So this is Tracerco Drum Vision. So on the right-hand side, you see the front face. That face will be flat against the coker wall or any other vessel that you intend to use it on. That essentially would be pretty close to the wall and at high temperature. On the left-hand side, that in the middle, you can see the rear of the Tracerco Drum Vision product. What we've got is the Tracerco swish on there, which sort of allows you guys to understand that it's a Tracerco product, and we're sort of marketing that. And then the 2 sort of cylinders at the back there, the detectors. To break this down, we look at the image on the left-hand side. So part 1, what we've got the face, the part of the Drum Vision product that actually goes to the face of the drum. So this houses the source and the detectors. It enables them to be optimized in certain distances between each other, and it allows for a bit of shielding from gamma at the front there. Secondly, we've got some neutron shielding. So at the front and foremost of it all, we do care about safety. Obviously, working with radiation sources, we're wanting the dose rates to be reduced so we can work with them efficiently and safely. So this part on point 2 is actually shielding for neutrons, which reduce the dose rate efficiently to a point where it's not going to affect workers around it, and work can be done quite easily around it. This also has an extra benefit to it. So unlike legacy systems where calibration is required quite frequently, this means that our product is constantly calibrated. We can actually track the neutrons and make sure that we're detecting them and there's no need for further calibration. Point 3, we can see our source holder. This is placed inside of the drum, and we can arm and disarm the unit by using this part. So when we actually wanting to go into the vessel or perform maintenance inside of a vessel, this can be disarmed and the dose rate at the front and in the vessel can be reduced. At point 4, we've got the nice looking shell. So this isn't just a nice looking shell, this is there for safety as well. So it allows for the user to lock the source in place in the armed or disarmed position, and it means the source cannot be tampered with. Point 5 is the main bit really. So we've got our detectors. These are solid state detectors. They don't need regassing. There's no hazardous material involved in these. And these actually determine what phase is what inside of the corker drum or any other drum that we're looking at. So that's it. That's drum vision. I've showed you the nice photos, but let's look at some data to show it actually works. So we've actually worked with a site in Europe. We've connected to the 4 to 20 milliamp system with our detectors, and we've been able to collect some data. This is just one cycle that we've got on the screen here. So the first 3 circles labeled anti-foam injection. We've seen foam rise to a point, and it's enabled the user to actually put anti-foam into the corker without wasting the anti-foam agent. And this can save time, save money, and make the process last as long as we can and optimize it so we can get the best output. Secondly, we can see the cooling water in the box. Essentially, the corker's been cooled down. We've been able to detect the cooling water that's gone in there, and that's clearly different to the foam and anti-foam areas as seen previously. Finally, we look at our 2 little peaks at the end, which are labelled water jet and the cork out. So as the water jets hit the part where we're detecting, you can see the spikes in the data. So this shows that the drum vision product is quite reliable and it picks things up quite quickly. So just to sort of summarise that up, drum vision is actually a non-contact product. There's no intrusion. It means there's no changes externally to the vessel of where legacy systems have been placed. No fouling or corrosion exposure. Secondly, we're looking at hydrogen-based measurements rather than density. So we're not looking from one side of the vessel to the other, especially in the case where corkers can be up to 10 metres in diameter. So what we're doing is looking 20 to 30 centimetres inside of the vessel, and we're seeing data from that. It's immune to dielectric and composition variation as well, and we can actually look at phases where there is a bit of an emulsion. That leads to the next point, unaffected by emulsion or foam. So we can accurately identify foam and emulsion phases quite clearly by the number of neutrons that we're seeing backscattered. These neutrons being different numbers at different points mean that we can follow it, and with the time that it takes to actually identify that, we can see a clear line of where changes occur. So it's also stable under process changes, so there's no recalibration needed. Essentially what we do is the corker is fitted with the drum vision product, and in cases where legacy systems have been placed before, it's retrofit and it can fit on quite easily. It's just a plug and play of the old unit. These units are calibrated to the hydrogen vapor and to water, so it will be a max and minimum at that point. And then from this, there's no need for further recalibration after that. Finally, I think we get to our main point where we're talking about safety, reliability and maintenance. So safety is our main point. We want people to be safe working with this, but we also want to be able to have a reliable product that helps you guys get the best out of your corker or other systems and get the best output. So we've used solid state detection, as mentioned before, where this requires no gas refills and there's no hazardous gas or material within these detectors. So we've taken existing neutron backscatter technologies, as explained by Logan earlier on in the presentation. We've created a fixed gauge that allows us to determine phases within the vessel and adapted our methods to create this fixed instrument. So there you have it, Tracerco's drum vision. I'll hand back over to Logan now to talk about applications and refining.
Yeah, thanks, Bailey. So we wanted to cover how drum vision can be used in a couple of specific refinery applications, delayed coking and distillation. So go ahead and get started with that. So we'll start off with delayed coking. So the challenge in delayed coking is that foaming in coke drums can cause an overuse of anti-foam. We all know that chemicals are not cheap. And it also poses a risk of carryover that can damage downstream equipment and downstream instrumentation. The limitations of traditional coke drum instruments are essentially that there is no reliable real-time measurement of the foam interface. So drum vision, using neutron backscatter technology, provides non-contact, real-time foam height and interface monitoring. Interface monitoring is a key here. Most traditional instruments that you're going to use here are level instruments based on density. If you look at hydrogen content versus density, you can see the actual interface. So the result of using drum vision here is reduced chemical usage, improved control, and better product quality. So how does drum vision solve this? We talked a bit already about how drum vision detects the difference in hydrogen intensity between the liquid, foam, and vapor in a coke drum. This leads to an early warning of foam approach, which allows operators to see exactly where the foam is in the vessel before it reaches the maximum levels, which allows for smart and timely anti-foam injection. The output of drum vision is quantitative feedback that allows operators to track foam collapse and liquid recovery, which in turn allows them to optimize chemical dosing instead of using a fixed rate injection. Drum vision data allows operators to act proactively instead of reactively on their coke drums. So the benefits of using drum vision on delayed coking start with process control, specifically optimization of anti-foam and preventing foam over events. Chemical consumption can be drastically reduced by injecting it only when the foam is detected. On top of that, early detection limits product loss, foam carryover, and potential operational upsets. The economic impact of just these two items can be incredibly significant in delayed coking operation simply by reducing chemical costs, avoiding an off-spec product, and of course, avoiding unplanned outages, which can be incredibly costly. I would like to point out that we do see gamma in a lot of coke drums. We understand that gamma is going nowhere. We use it and provide it ourselves, but drum vision is intended to overcome or complement some of these disadvantages and challenges of gamma-based measurement, especially in interface measurement of large diameter, thick-walled vessels. Next, we're going to talk about distillation. So the challenge in distillation applications is that conventional level instruments struggle with emulsions and density changes in distillation systems. Traditional level instruments can drift or foul, which requires frequent recalibration and the risk of an off-spec product. Drum vision and neutron backscatter provides a stable, externally mounted interface measurement that works independent of process conditions. Drum vision is less affected by fouling than traditional instruments due to being a truly external, non-contact measurement, and due to the mechanism of measurement, which is hydrogen concentration. The result of using drum vision is better separation control, reduced corrosion, less planned and unplanned maintenance, and of course, improved product consistency. So how does drum vision solve this? Well, first off, it's immune to density and dielectric changes. Again, drum vision measures hydrogen content, and the instrument is not affected by temperature or density changes, unlike other conventional instruments. Drum vision gives a continuous, real-time response, which allows operators to understand and control the interface in a distillation column using real-time information. Also, as a side note, to install drum vision, there are no internal penetrations or major modifications required to put it onto the vessel. Some of the primary benefits of using drum vision are listed here, including operational reliability. Using this technology will give you consistent readings even when your inputs change, which will reduce the need for manual intervention and calibration. It can also provide energy efficiency by reducing the demand on the reboiler. If levels are too high or too low due to conservative operation, the tower may experience entrainment or weeping, which forces the reboiler to work harder to maintain separation specifications. Long-term, this leads to lower maintenance and shutdown costs, and as we mentioned previously, you've increased your operational insight and data in real time that can help you optimize your process. So why does precision interface measurement matter? It directly impacts your product quality, energy efficiency, and equipment integrity. Better measurements result in better yields, lower costs, and safer and more predictable operations. Regardless of your job title, unit, or facility, it's safe to make the assumption that every one of you in here shares these goals. So with that, we're going to conclude the presentation on non-contact interface measurement and refining and the introduction of drum vision, which allows you to see more, control more, and save more. You cannot measure what you cannot see. And on that note, I'll invite Bailey and Neil back to the chat, and we will take some questions and provide some answers.
Hey, thanks so much, Logan. I'm going to step in as well. I'm going to just get rid of the slide here. We don't need to look at that for forever. I'll put us up on camera, and let's start going through some of the questions that have come in. I saw Neil was answering some of those in the background while you guys were talking. I may pull out a few of those just so everybody can benefit from the answer there. The first one I'm going to pick is how many units can be installed on a drum? And somebody just jump in and say, I'll take that.
Yeah, I can take that. So typically, if we look at a cork drum type application, it would be anywhere between 3 and 4. The lower one would be situated around the bulk level of the cork to monitor the high level of the cork and the low level of the foam. And then the other 2 or 3 would be placed further up, like Bailey and Logan mentioned, to measure the foam approach and to optimize the anti-foam dosing regime.
All right. What is the response time to internal fluid changes?
So I'll pick that one up. The response time can vary. It depends on sort of how we change that. So we can put that in and choose a response time. So we can have a short response time, which would likely have more errors, or we have a longer response time, which would have less errors. So what we've done is we've put 2 detectors in there to reduce error overall, so we can actually reduce that response time. So we're looking at about 10 seconds to 30 seconds, or potentially even quicker in some cases.
All right. Are there any special maintenance requirements?
I'll pick that one up. So no, there isn't any special maintenance requirements. What we've done is we've sort of set up so as we've got solid state detector, we don't have any refilling of gases like legacy systems. Once calibrated, there's no need for further calibration, and there's no servicing needed on it.
All right. We had a couple of people asking about the working life of the neutron source. Is there an average amount of time that'll stay good?
Yes. So we've looked at the legacy systems to see what they were using. That's about 15 years. We've actually doubled that. So the neutron sources that we're looking at using are 30 years till they need recycling.
If we have an old Krill Pro, can this replace it, and can Tracerco remove and recycle?
Yes, so absolutely. So we've designed this so it's a retrofit system that's just switching out the Krill Pro and putting our unit on. We've got the same bolt holes, stud holes on there, so we can do that. I think in most cases we can look at having a third party to recycle the Krill Pro. But yeah, essentially it's a plug and play, and we can connect straight up to the 420 and you'd see exactly what you'd see with the Krill Pro if not there.
All right. Does the detector lose efficiency over time, and do we have to worry about hazardous materials in the detector?
No, so again, going back to the solid state detector versus a gaseous detector. So we are actually using a solid state detector where there is no hazardous materials involved. So there may be legacy systems including boron trifluoride, which is a poisonous gas. We don't have anything like that. We don't have a loss of gas, and our detectors stay as efficient as they are from day one.
All right. We had a question about diameter. What's the diameter threshold that would make a gamma scan unreliable?
Yeah, I'll pick that one up, Ken, because I answered it. So the main, I think the driver for that question is looking at measuring interface with gamma. So that's about having enough energy through the lighter phase to measure a signal change in the higher density phase. So when you get onto very large diameter vessels, like Bailey mentioned, some of the cork drums and the distillation towers are sort of 6, 8, 10 meters in diameter, the amount of gamma energy that you would have to have externally to pass through that would just be impractical for any kind of normal use. So typically sort of 600 millimeters to a meter, but it does depend on the wall thickness and the process densities. But it's all about ensuring you get enough energy change through those different process fluids to a detector mounted externally.
Okay, I have follow on. This seems to be a very similar type of question. It's asking about temperature and pressure considerations. Do those act as limitations for drum vision use?
I can take this one. So unlike other systems, we actually have temperature compensated our detectors beforehand. So as temperatures change within the Corker system, we actually change the bias or the voltage in the detector so that the peak that we are wanting to see stays in the same place, meaning that we don't have any issues when temperature changes, and pressure is not a problem at all. We've got a hazardous area certified detector that we use, so there's no change.
Okay. On an external tank or vessel, would rainwater affect your measurements?
I think that's a great question. So what we're looking at doing is putting a hood over the device, essentially. So this hood would stop the rainwater going down the side of the vessel, and we wouldn't have a problem with rainwater at all. And also what we're looking at is the shielding that we've got on the outside of the unit, as I shown earlier. That also means that any person or any weather event that might go past the back of the unit does not affect it either.
Can I just add to that, Ken, just in case the raining is referred to as internal to the vessel in terms of the process? The hydrogen concentration of any fluid raining in the gas phase would be different to that we would see of foam. So we would be able to compensate and obviously measure accurately for that.
Great. Thanks, guys. Okay, I have a question about accuracy levels or tolerances of the readings that you can get.
So what we've got is we differentiate between the hydrogen materials I've explained before. So because of the different hydrogen in the process materials being so different, we can actually accurately differentiate between the phases quite clearly.
All right. I had a question about applications. Would this be applicable for offshore oil gas multi-phase separators?
Yep, I can take that if you want, really. Yes, absolutely. So any process that has 2, 3, or multiple phases that require separation, we will be able to see and differentiate those phases. So solids, sand, mud, oil, emulsion, rag, water, foam, gas. We can see and differentiate between all of that.
All right. Let's see. This is more of a general question. Can you compare neutron backscattering technology to gamma ray LTs? Do you see one technology dominating and the other one retreating?
Yeah, I can take that as well. It depends on the application and what the desired measurement is. So like Logan alluded to earlier in the presentation, Tracerco, we also supply gamma measurements. They're typically used externally for bulk liquid level measurement. So when we're looking at large diameter vessels, like the question I answered earlier, you need to ensure that we're having enough energy change between liquid phases, and that becomes impractical measuring externally with an external radiation source and external detector. So this is where drum vision and specifically neutron backscatter technology comes into force.
All right. Well, you have been so incredibly efficient that we made it through every question that was typed in. PTQ Magazine and Digital Refining hope that you found this webinar useful and informational. On behalf of Tracerco and the entire team here today, thank you. We appreciate your participation and all the great questions we got, and do enjoy the rest of your day. That concludes our session.